Hello guys, today I am going to explain the Bell-Coleman cycle or the reverse Brayton cycle or the Joule cycle. In this video, I will explain about the different components of a Bell-Coleman cycle, the processes involved in the Bell-Coleman cycle, and to draw the PV as well as the TS diagram of a Bell-Coleman cycle, and I will discuss the derivation of the COP of the Bell-Coleman cycle. First of all, there are four major components that are involved in a Bell-Coleman cycle. First one is a refrigerator, then compressor, a cooler, and expander. As the name indicates, the function of a compressor is to compress the refrigerant to a higher pressure. The function of a cooler is to cool the refrigerant to a lower temperature. The function of an expander is to expand the refrigerant to a lower pressure. And the refrigerator, it is a chamber where we need less temperature. That is, this is a chamber to be which cooled. So the process involved in the Bell-Coleman cycle can be explained with the help of this diagram, and I will explain the PV and TS diagram with this explanation. So first of all, consider the refrigerant 4. This is the state of the refrigerant. 4 is one of the state of this refrigerant in the cycle. So when the refrigerant moves through the refrigerator, it will absorb heat from the refrigerator. The refrigerant will absorb heat from the refrigerator and it will evaporate. And the refrigerant which is at the evaporated state will pass through the compressor. As I said earlier, the function of a compressor is to compress the refrigerant to a higher pressure. So 1 to 2, the compression takes place. We need to understand that the compression takes place in isentropic fashion. That is, no heat is added, no heat is absorbed from this compressor. So the isentropic compression takes place in the compressor. So we can discuss the TS and PV diagram of this process. That is 1, 2. Let the state of the refrigerant at 1 be like this, and from 1 to 2, isentropic compression takes place. We know that in a PV diagram, isentropic compression is denoted by this fashion. In a TS diagram, the isentropic compression is denoted by this fashion. That is, the isentropic means entropy doesn't change. That is, entropy of 1 and 2 are equal, so that entropy, so this will be parallel to the y-axis in a TS diagram. So 1 to 2. So this compressed refrigerant will pass through the cooler. The function of a cooler is to cool the refrigerant. As we can see, the water is provided into the cooler and is taken out of the cooler. So the water will absorb the heat from the refrigerant, and the refrigerant will cool to a lower temperature. So the refrigerant, but we need to understand that this whole process is happening in a constant pressure. So 2 to 3 cooling will take place in an isobaric process, which is an isobaric process. So we can denote it in PV as well as TS diagram. So in PV diagram, state at 2 is marked here. From 2 to 3, it is an isobaric process. So cooling happens. Cooling means volume reduces, so that in an isobaric process, the pressure remain constant. 2 to 3, volume is reduced. So in a TS diagram, here the cooling takes place. Cooling means temperature is reduced. So from 2 to 3, temperature is reduced, and this follow in a isobaric. This follow a isobaric process. That is, in a TS diagram, constant pressure lines are denoted in this fashion. There are a lot of infinite number of constant pressure lines in a TS diagram. 2 of the pressure lines are denoted here, 4 to 1 and 3 to 3 2. So from 2, the process is isobaric and cooling takes place. So it will follow a constant pressure line, and it will cool to a temperature of T3, or it will reach the state of 3. So cooling happens, and after cooling, it will be delivered into an expander. So the function of expander is to expand the refrigerant in the system. So 3 to 4, expansion takes place. Expansion means the pressure is reduced. From at 3, the cooling happens and the refrigerant will be in a liquid fashion, in a liquid state, sorry, in a liquid state. So this liquid will be get expanded. So expanded means the pressure is reduced from 3 to 4. The pressure is reduced in a isentropic fashion. This is more important. In a compressor and expander, the process are in isentropic fashion. From 3 to 4, the isentropic process, which is a expansion process. 3 to 4 in a PV diagram, we denoted the isentropic process, which is a expansion process, that is pressure is reduced from 3 to 4, that is P3 is greater than that of P4, pressure is reduced. In a TS diagram, it is isentropic process, that's entropy doesn't change, and in an expansion process the temperature is reduced, so that it is represented by this line 3, 4. The refrigerant which is passed through the expander is expanded to a lower pressure, and then it is passed to the refrigerator. In a refrigerator, the process will be denoted by this, that is, it is also isobaric, like cooler. In a refrigerator, heat addition is also isobaric process. So from 4 to 1, it is isobaric process, heat is added, it become vapor, so that volume will be increased. So 4 to 1 volume is increased, and in a TS diagram it can be represented as the isobaric process. It will follow a constant pressure line, and it will reach to 1 from 4 through a constant pressure line. So this is the basic process involved in a Bell-Coleman cycle, and we can find out the COP of the cycle, that is heat added. Where is heat added? Heat is added in the refrigerator. It is added to the refrigerant in the refrigerator. So it is a constant pressure process. So heat added in a constant pressure process is denoted by Cp into T1 minus T4. That is 4 to 1, it involves heat addition. So 4 to 1, it is heat addition. So Cp into T1 minus T4, it is the heat added. Where is heat rejected? Heat is rejected in the cooler. So heat 2 to 3, it involves heat rejection. So heat rejected is denoted by, it's a isobaric process. So heat rejected is Cp into T2 minus T3. Okay. We know that COP is defined as heat added to the work done. So what's the work done? Work done is given by heat added minus heat rejected. These are all the basic concepts. So we can write it as QA by QB minus QA, and substituting QA and QB from this equation to this equation, we will get Cp into T1 minus T4 divided by Cp into T2 minus T3 minus Cp into T1 minus T4. So Cp will get cancelled, and so Cp will get cancelled from numerator as well as denominator, and taking T4 outside, we are taking T4 outside in the numerator, so T1 by T4 minus 1, taking T3 outside from this denominator, so T3 into T2 minus T3 minus 1, minus taking T4 from this term, T4 into T1 by T4 minus 1. So we get an interesting relationship between T1 by T4 and T2 by T3 if we consider the processes. So consider process 1 to 2. This is an isentropic process. So we have pressure ratio, the relationship between the temperature ratio and pressure ratio as T2 by T1. T2 by T1 is equal to P2 by P1 whole raised to gamma minus 1 by gamma. Okay. We also have another isentropic process from 3 to 4. So applying similar equation, T3 by T4 is equal to P3 by P4 whole raised to gamma minus 1 by gamma. So the interesting fact is that P4 and P1 are equal. That is, P4 and P1 are equal. P2 and P3 are equal. P2 and P3 are equal. So this term and this term are equal. That means T2 by T1 is equal to T3 by T4. Rearranging it, that is taking T1 here and T3 here, we will get T2 by T3 is equal to T1 by T4. So T2 by T3, that is T2 by T3 is equal to T1 by T4. T1 by T4, that is T1 by T4, T2 by T3, and this is also T1 by T4. These all are equal, so these will get cancelled. So we will get T4 by T3 minus T4. T4 by T3 minus T4. And we are again dividing the denominator numerator with T4 because we need a ratio. That is our final objective. So dividing the numerator with T4, we will get 1. Dividing denominator with T4, T3 by T4 minus 1. This T3 by T4 is already found out, that is P3 by P4, all raised to gamma minus 1 by gamma. Substituting this, we will get this in this fashion. So observing P3 and P4, that is P3 and P4, or it is equal to P2 by P1. This P3 by P4 is defined as the compression ratio. It is defined as the compression ratio or expansion ratio. So it is denoted by RP. So reducing it into the form of RP, we will get 1 by RP whole raised to gamma minus 1 by gamma minus 1. This is the final equation of the COP of a Bell-Coleman cycle. So these are the basic concepts behind the Bell-Coleman cycle. So if you found it helpful, please like this video and subscribe my channel. Thank you.